Hi and welcome to this clip on the redox reactions of some common transition metals. It'll stick to the main reactions that are covered in the A-level chemistry specifications from 2015 onwards. The clip's mainly designed for second year A-level students and it's best viewed and looked at once you've covered transition metals and redox to second year A-level standard. So to get towards the end of the clip, what we'll look at is how we might apply some of these ideas to short and long answer exam style questions. So let's start with iron 2+ and iron 3+. So to start with, when we add some Fe2+ solution to manganate, it's oxidized to Fe3+. Now initially it doesn't seem like much is happening, but when you add slightly larger quantities, you can see that the colour starts to disappear. And what you're left with is the orange colour of Fe3+. And if you put the colours underneath each of the species in the equation, the overall equation, you can see quite easily what's happened. And we can back this up by looking at the electrochemical data for each of these half cells. It can clearly be seen that the manganate half cell, manganate 7 to manganese 2+, is plus 1.33 volts, which would mean that it stays as a reduction, as you can see in the purple equation towards the top of the screen. If you look at the blue equation towards the top of the screen, both to the right of the photograph where the video was playing, you can see that the iron 2+, iron 3+ redox system has been reversed in order for this to actually work. And at the top of the screen I've put some of the synoptic links you can expect to find throughout this clip. So let's now look at the other way round for iron. Instead of iron 2+ being oxidized to iron 3+, iron 3+ being reduced to iron 2+, this requires a different set of reagents. So this time we can take some iodide ions and add them to Fe3+. And what you'll see as soon as there's enough of it there is you'll get a brown colouring towards the top of the liquid. And that brown colouring is the formation of iodine. At the same time, we'll obviously be forming some pale blue Fe2+, but unfortunately that colour of that is masked a bit by the presence of the aqueous iodine. So we'll do the overall equation for this in a moment as well. And if we put the colours underneath the species again in the main equation, I haven't put a colour underneath iodide because clearly you can see from the photograph that it's colourless. So the brown colour indicates the formation of iodine. It's difficult to tell that Fe2+ is there because obviously pale green will be masked by a stronger colour, darker colour like brown. But we can again use electrochemical data to support what we're doing here. And again, if we compare them, we can see quite clearly which one is more positive. So you can see clearly that the iodide is oxidized because its electrode potential is more negative. So when it's put in the presence of Fe3+, the Fe3+, Fe2+ redox system remains as a reduction because it's got a more positive electrode potential, plus 0.77. The iodide electrode potential of plus 0.54 volts is more negative. So what happens here is it's oxidized, so the equation is reversed. So let's now have a look at chromium-based ions, Cr2O7, dichromate 6 I should say, and Cr3+ chromium 3. So let's now have a look at dichromate being reduced to Cr3+. On the far left I've got a video clip I'm about to play. And here what I'm doing is I'm adding zinc powder to dichromate. So what it's doing is it's behaving as a reducing agent, so you can see an instant change in colour. So you can see the dark green colour change from orange to dark green. That shows that the dichromate has been reduced. we used zinc metal in the form of powder as our reducing agent. But what you have to be careful of is the number of electrons that are needed for the reduction of the dichromate. So there's actually quite a lot of zinc that's required. So I'm giving the test tube a shake to see if we're getting a reasonable colour change now. So you may see now that it's against the light, it's gone even further to a blue colour. This shows another colour change. So just multiplying the zinc half equation up by 3 so that we have our 6 electrons that we need. So in the second clip what I'm doing is adding some zinc granules instead to a second sample of Cr2O7 2-. And you can see quite clearly that the reaction isn't anything like as quick as in the first video clip. So you can see in this second video clip that we have the same sample of Cr2O7 2- has now become Cr3+. And you might notice it's taken a slight blue colour. I'm going to come on to that in a second, because it's actually a further reduction that's taken place in the presence of the zinc powder. So I'm trying to add a reasonable amount of zinc granules here so that I can have as much zinc as possible to get the reaction going. It doesn't seem to be doing much at the moment, so we'll just pause the clip for now. So if you look at the original sample, this one here, you can see that it's actually gone pale blue quite clearly. Now, even still, the second sample isn't doing much. I'll give you a quick shake to see what it's going to do. Nope, nothing so far. So what I decided to do is add a little bit more sulfuric acid, so acidify it a little bit more to try and encourage the reaction to go, because obviously, as you can see, quite a lot of acid is needed. So it still doesn't not do much for that particular clip, but you might be guessing already that the third clip, which I haven't started playing yet, is the same sample I've just been shaking, but 5 minutes later. So this time you can clearly see the change in colour. So what's happened here is it's turned into the dark green Cr3+. So if we now insert the electrochemical data, just like we did before, we can write out 2 overall equations. One overall equation for the reaction between chromium 3+ and zinc, and one overall equation for the reaction between dichromate 6 and zinc. So the dichromate reduction down to Cr3+ remains as a reduction in the presence of zinc because its electropotential is definitely more positive. But what about the second reaction, the one in the bottom right-hand corner? In this case, minus 0.41 is more positive than minus 0.76. So the chromium 3+, chromium 2+ redox system stays as a reduction compared to the more negative zinc. So that must mean that zinc is the most powerful reducing agent. So as a result, it gives rise to the multiple reductions of chromium that you've seen in the clips. So we're now going to look at reactions of copper ions, and including in that is the idea of disproportionation. So as you can see, that means that it's a redox reaction, but an element is reduced and oxidized. And it's important to remember that it's actually the same element that's being reduced and oxidized simultaneously. So initially, it would look like that's the kind of combination you get, Cu2 plus E minus giving you Cu plus, and in the oxidation side, 2I minus giving you I2 plus 2E, 2 electrons. So let's have a quick look at the video clip and then work out what's going on. So I take some iodide ions in solution and add them to Cu2 plus in solution. Initially, you'll be able to see the formation of iodine in solution, but also it goes quite murky. So it's not just a solution, there's a precipitate happening as well. So that precipitate is something called copper-1 iodide. So we're not just having a simple swap of ions here, we're also having copper-1 iodide precipitate formed as well as iodine. So the overall equation needs to take that into account. So I'll just pull the test tube over to the camera so you can see it a bit more easily. So you can see quite clearly it's not just a solution, there's some kind of precipitate formed because the liquid isn't clear, it's opaque. So what happens is you get an overall murky brown appearance due to the combination of a white precipitate forming plus the brown iodine. Now eventually the precipitate will settle and you'll have the sort of clear solution of iodine in a sort of a brown solution colour. Brown solution colour? A brown coloured solution instead, but I didn't have time to film that happening because it takes a little while for that precipitate to settle. Let's now have a look at the disproportionation reaction of Cu+. So what we've got here is copper 1 oxide. So copper's in the +1 oxidation state. So what I'm doing as the reaction proceeds is actually showing the oxidation numbers that show what's happening. So as we add it to H2SO4, it's in a warm water bath. You may be able to see the slight condensation on the this part of the beaker. So what happens is you have simultaneous reduction and oxidation. Of your copper. So going from +1 to 0 in the copper solid and +1 to +2 in copper sulfate. So you can probably see already a colour change right at the bottom of the test tube where it's gone blue. And if I leave it for a little bit longer, what will happen is you'll also get copper solid being formed on the surface of that clump of copper 1 oxide. So I'm going to break up the clumps a little bit to allow the sort of blue colour to become more apparent. So you can see that the blue copper sulfate is now spreading as it's formed, it dissolves in the water, it diffuses. So you can see that the actual water itself now has a blue tint, which is the copper 2+ ions from copper sulfate. So you may just about be able to make out a pink sort of colour at the bottom of the test tube. So I'm going to try and position the test tube so the light from the window is actually shining on it a little bit better. So I'm going to move the tablet around. And hopefully now you can see the pink colour at the bottom. So that pink colour is the copper. So it shows that two products have been made from the original red copper 1 oxide. So let's now have a look at some past paper style questions. So I've selected a fairly sort of synoptic question that goes back over a fair amount of things to do with transition elements, not just one particular aspect. And it's also got some calculation work, as you can see towards the bottom of the page, on something that you might not have heard of before. So we'll start off with the straightforward stuff. It gives you some information about iron, saying that it shows more than one oxidation state in its compounds, and it says that its compounds are used as catalysts. So it gives you some information that about the behaviour of iron that shows it's a transition metal. So the first thing it wants you to do is to do the electronic configuration for an iron 3 ion. So that's essentially an iron atom with 3 electrons removed. So essentially what you've got to do is empty before S2 orbital, and then another electron from 3D can be put in there, or removed rather, I should say. So that gives us 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Now I need to use this to explain why iron is a transition element. So in other words, what's going on is you've got a partially filled subshell. So now we need to do a little bit of recall in part B. So I would basically state the Haber process here. We've looked at it enough times. You've looked at it at GCSE, and this is where you recall it. So the name of the catalyst is just straight iron. It's not even a compound of iron. And it catalyzes the production of ammonia. I've just decided to give the equation there because that's the most straightforward way of saying it. So then it says, under certain conditions, iron can be oxidized to form sodium ferrate, and it gives you the formula, Na2FeO4. And it gives you some information about it, likening it to potassium manganate, which we looked at a little bit earlier in this clip. So this takes you a little bit out of transition metals. This is a bit synoptic here. And it's got some application as well, because it applies empirical formula calculations to a new compound that you haven't seen before. So let's move the page down and give it a go. So the first thing you can do is you can get the ratio, the rough ratio, by taking the percentage that the element's found in divided by its relative atomic mass. That gives us 1.21 for sodium, 0.60 for iron, and 2.41 for oxygen. So you divide by the smallest. So that gives us Na2FeO4. So moving the question down, and it says deduce the oxidation state of iron in sodium ferrate. So taking sodium to be +1 and oxygen to be -2, it must mean that overall the, dropped my calculator there, for the compound to remain neutral, you must have an oxidation state of +6. So we can put that in. So movage. It tells us the half equation for the reduction of ferrate ions in acidic conditions is shown as on the screen. And it says acidified FeO4 ions oxidize aqueous iodide ions to form aqueous iodine, which is I2. So it asks you to construct the half equation for the oxidation of iodide ions to form iodine. So it's a little bit like the reaction we did earlier with copper, apart from this time it's talking about iron, so it's mixing and matching it up a little bit. So it's still quite applied, this. It's not going to be in your textbook, but it's definitely within your grasp if you just keep a cool head and think about what they're asking you. The next thing to do is to construct the ionic equation for the redox reaction that occurs between aqueous FeO4 and aqueous I- in the presence of H+. So you've got the two half equations. All you really have to do, so what you've got to do is to multiply the half equation that you've just constructed by 2 so that it actually has 4 electrons. So therefore the 4 electrons in the half equation that they've given you can actually be cancelled out. So I normally put in state symbols just to be on the safe side, even if they don't ask for them in an overall equation, because then it actually shows what's going on and in what state everything is. So the colour change you would see when aqueous FeO4 is added to an excess of aqueous I- in the presence of H+. So they want you to predict that. And if you remember earlier on in the clip, we talked about iodine being a brown colour and iodide ions being colourless. You saw in the clips that I embedded into this video. So it shouldn't be too difficult to work out what goes here. So they didn't ask us to say anything about whether it was a solution or not, but I put that little bit extra in because we've seen it in the clip today. So colourless solution to brown solution. You could say orange or dark brown or light brown, but you must have brown, I think, in there somewhere. I've just realised I'm actually going to change my mind on that, because iodide, although iodide is colourless, the question itself said that the ferrate ion, the sodium ferrate, is a red-purple coloured substance. But the part that's really important is the brown solution. So I put a little footnote there just to explain what I meant. Right then, let's go on to the next question. And this is a longer answer one. If we bring the page down a bit, you'll see it's 11 marks. So it tells you specifically what to do. So I'm going to start by splitting my answer into 3 sections. So just by doing those three subtitles based on the 3 bullet points, I now have a plan. I've broken up the job into 3 sections to make it easier to actually deal with. So the first thing I'm going to do is the bonding and shape of one of the complex ions. I'm going to go for 2+. So I started by drawing the diagram of the octahedral complex FeH2O6 2+. I've got my square brackets, I've got my charge, I've got my correct shape drawn in, and I've got the bond angle mentioned, and I've mentioned the shape by name. The type of bonding is coordinate, but it says describe and explain. So I'm going to do a little bit above just to explain. So the oxygen atom in the H2O ligand donates lone pair of electrons to Fe2+. So starting with the isolated H2O gaseous molecule, you do a count of the lone pairs and bond pairs. You state that lone pairs repel more than bond pairs, giving a 104.5 bond angle, 104.5 degree bond angle for hydrogen, oxygen, hydrogen. So the H2O ligand has 1 lone pair and 3 bond pairs, including the coordinate bond we just discussed in the previous part of the question. So that would make the bond angle 107. And I thought I'd put the reason in, which is that it's less repulsion between electron pairs. So basically we're looking for a chemical test that can distinguish between Fe2+ and Fe3+. So one chemical test might be the addition of sodium hydroxide solution and seeing what colour precipitate you get. But we've looked at another one in this particular clip, haven't we? That actually isn't in the mark scheme for this older question. And that's the reaction with manganate or iodide. So we've looked at that one for Fe2+. We've also looked at the reaction between Fe3+ and iodide. So although this second set of chemical tests that are specific to this video clip aren't only for Fe ions, they could be used to distinguish between Fe2+ and Fe3+ if you happen to know that the 2 solutions you had were Fe3+ or Fe2+. However, it's generally regarded that the addition of sodium hydroxide or hydroxide ions to Fe ions definitely gives a light green precipitate with Fe2+, and definitely gives an orange precipitate with Fe3+. So that's more a sort of diagnostic test for iron itself. If you know that your 2 solutions are iron, but you don't know which one is 2+, which one is 3+, you could do the manganate or iodide test if you wanted to. Okay, so hopefully this has been a reasonably useful synoptic review of several areas as applied to transition elements. But thanks a lot for your time, thanks for listening in, and see you soon.